Hi, I'm Farhana. Thank you for joining me in this lesson. We'll be doing some work on trigonometry rules, and specifically, we're focusing on three-dimensional trigonometry. Let's have a look at our concept map first. Okay, so far we've covered solving non-right angle triangles in the sessions before this. We've covered sine rule, cos rule, and area rule, and we've also covered the proofs and applications. This time we're focusing on 3D problems. Before we begin, let's do a quick recap of all the rules and when to use each rule. So, let's begin with the sine rule. Okay, what is the sine rule? The sine rule is sine A over A equals sine B over B equals sine C over C. And we have the reciprocal versions, which we use when we're looking for a side, and it's A over sine A, B over sine B, C over sine C. And can you remember when we can use the sine rule? We're allowed to use the sine rule when we have, that's correct, when we have one full pair of sides and angles. Okay, so if we look at this diagram here, let me just grab my pen quickly. Okay, so you must be given A and angle A and the side across it. Any full pair like that where you have one angle and its matching side, then we can use sine rule. Okay, so basically we can use sine rule when we have angle, angle, side, or side, side, angle, and remember in this case, it's not the including angle. Okay, we have the sine rule, the ambiguous case. Can you remember when we have the ambiguous case? It's when we have two sides and an angle, but the side given opposite the angle is the shorter of the two sides. So in this case, 6 is the shorter side. So in this case, 6 is less than 10. So we will have the ambiguous case. And remember, we can draw two different triangles for this with the same information. Okay, and our next rule, area rule, this is an easy one. Remember, we're looking for a kind of a V pattern when we're doing area rule. So we need to have half AB sine C, half BC sine A, and half AC sine B. Okay, and you use area rule when you have side, angle, side. So basically, you can use it when you have AC and the sine of B. So we're looking for the V pattern. Okay, and when do you use the cosine rule? When you have two sides and included angle. So what is the cosine rule? A squared plus B squared minus 2BC cos A. B squared is equal to A squared plus C squared minus 2AC cos B. And can you remember the last version? C squared is equal to A squared plus B squared minus 2AB cos C. Okay, and remember, we can also use the cosine rule when we want to find an angle. All we do is just rearrange the equations we had in the last slide, and then we can find our angles, A, B, and C, using this version of the cosine rule. In this case, remember, we have to be given the three sides to find one of the angles. Okay, and then when we're deciding which rule to use, hopefully you can remember this. We've been through this in the previous sessions. Okay, if it's a right angle triangle, then we ask if it involves angles, and if it does, then we use the trig ratios, sine, cos, and tan to solve it. If it involves no angles, it only has sides, then obviously we're going to use theorem of Pythagoras. Okay, if it's not right angle triangles, then we've got to look at to see if we have one full pair, an angle and its matching side, and if we have the angle and its matching side, then we can use sine rule. Okay, and if we don't have a matching pair a matching pair of an angle and its side, then we've got to use cos rule. And remember again, sine rule is used when we have angle, angle, side, or side, side, and not included angle. And cos rule is used when we have side, angle, side, or side, side, side. And remember, in cos rule, we're looking for that V pattern. Okay, hopefully you remember all those rules that we've done before and when to apply them. Let's look at our first three-dimensional drawing in this example. So we have a cuboid here that's drawn with its measurements as shown. calculate the length of BD. The second question, calculate the angle between BH and the base of the cuboid. Now, before we begin, we need to understand the different planes that are present in this figure because it will help us understand which angles are right angled and which are not. Okay, so if we look at our cuboid, you'll notice as it stands, we have a vertical plane in front, we have another vertical plane at the back, we have this plane, and this is a horizontal plane. The top and the bottom are both horizontal planes, and then we have two more planes, that's the one on the right, and this one here at the back. Now notice something, a lot of the diagrams that you will see in 3D trigonometry will kind of remind you of a corner of a room. So if you look at this room that we have here, we have that line and that corner here. Okay, so this wall here, if you remember it as looking like a wall, is always right angled because this plane, the plane where the wall is sitting on, is perpendicular also to the plane of the floor. And similarly, this angle here will be 90 degrees. Okay, so picturing a corner of a room kind of does help us when we're doing 3D trigonometry, as you will see a little bit later. Okay, so now they've asked us to calculate the length of BD. And BD is this line sitting on the base of this cuboid here. And because it's lying on the base, we realize that this angle here is 90. And because this angle here is 90, we actually have a right angle triangle. And because we have a right angle triangle in triangle BAD, we can then use grade 9 theorem of Pythagoras to solve it. So it becomes pretty simple from here on. And remember, here's our right angle triangle. And we've got this side is 7. And this side here is the same as this. So they both are 4 centimeters. And there's our 4 centimeters here. So now we have to solve this using Pythagoras. This is pretty simple, grade 9 work. You'll say BD squared is equal to AB squared plus AD squared. And that's going to equal to 4 squared plus 7 squared. And your answer is 65. But remember, we're looking for BD, so it's the square root of 65. Okay, that should have been simple enough. Let's go to our next question. Now they've asked us to find the angle between BH, which is this line here, okay, and the base of the cuboid. So they want the angle between that and that. Now remember earlier we found this BD to be square root of 65. Okay, so because that's square root of 65, and this is a vertical plane, it's perpendicular to the horizontal plane or the floor of the cuboid. So basically now we have a new right angle triangle in BDH, and we want to solve this, which is the hypotenuse. So if we redraw this, and it does help to redraw the triangle separately with the information you want, just so you can make sure you understand where the right angle triangles are. Here's a drawing. Okay, so BD is root of 65, and here's our right angle triangle, and DH is 6 centimeters. And again, the calculation is easy, just to visualize where the triangle is sitting. I think that's the part that requires a bit of skill and getting used to. And now we just do Pythagoras again. Sorry, now we want to find the angle, apologies. So we've got to use, we have the opposite and the adjacent, so we're going to be using tan of theta, because tan is the ratio that has opposite and adjacent. So it's going to be 6 over 65. Okay, and then you're going to use your calculator to say shift tan, 6 of 65, and you've done this a lot in grade 10 and 11, so you know how to find the angle then, and so you'll get the angle to be equal to 36.7 degrees. So it means that this angle here is now 36.7 degrees. Okay, we're going for a quick break. I'll see you after the break. Okay, welcome back. Before the break, we were dealing with 3D trigonometry problems. So we will continue with that. Let's look at our first example. Okay, in this example, it says the Great Pyramid of Giza is a square-based pyramid with a side length 230 meters and it's 139 meters high. So what they're telling us is we've got a prism and the base, the gray area, is square, which means every corner is a right angle. So that's a right angle, and that's a right angle, and so is that one. Okay, and they've given us that the sides are 230 meters, and that applies to all sides because it's a square-based pyramid. So all four sides will be equal. And they've given us one additional piece of information. They've given us the height. And the height is this line here. And they've given us the height to be 139 meters. Okay, so if you can picture the pyramid, and that's the height that's drawn there, that's drawn from the apex of the pyramid to the base of the pyramid. And this line that joins the height of the pyramid to the base will usually meet right at the center, and it will be also 90 degrees. Okay, and we'll discuss that a little further when we're doing the second question. The first question they ask us, though, is calculate the length of the diagonal of the base of the perimeter AC as shown. So the first question tells us they want us to calculate this length, the length of AC. And you can see it's going to be a pretty simple calculation because we have a right angle triangle ABC here. And we have the two sides, so we can probably just use Pythagoras to complete that one. The second one says, if you were to stand in one corner of the pyramid and walk up to the top of the pyramid, what angle would you be walking up at and how far would you have to walk? Okay, let's first answer the first question and we get to the B as soon as we're done with that. Okay, so to find AC, again, we did say it's going to be a right angle triangle. And specifically, it's going to be a right angle triangle with our two sides being 230 and 230. And it just means we've got to apply Pythagoras, which is pretty simple. So AC squared, the hypotenuse will be the sum of the two sides squared. So 230 squared and 230 squared. We've got to add them together, and we're going to end up with AC squared is 105,800. And then we end up with AC being roughly around, sorry, I should have actually have a unit there. So it's roughly around 325,27 meters if we're rounding off to 2 decimal places. Okay, so that was pretty simple. Okay, let's get to the second question. And the second question was asking us, if we were to stand in one corner of the pyramid, so basically if we're standing here, and we walked up the pyramid like this, what angle would we be walking at? So they want us to calculate this angle here that's labeled theta. What angle will we walk in? So it's from the base of the pyramid, from the base of the pyramid up to this line that's joining A and M. And they're asking us how far we would have to walk and what is the angle. Okay, so let's begin by finding the angle. Remember, we've already found that AC is 325,27 meters. And we're going to need that because if the whole diagonal is 325 meters, that means this point here N will divide the line in half. So AN will equal to NC. And that's where we're going to begin our calculations because if we look at the triangle that we're trying to find, it's this pink triangle here. So we're going to use this triangle, AMN, which is a right angle triangle. Here's our right angle. Remember I showed you earlier, it's sitting there. And we can find AN. And because we have theta, and this is a right angle triangle, we only need 2 bits of information. So we have an opposite side, and we have this, if we find this adjacent side, then we can use our tangent function to solve for theta. So let's write that out. Okay, so here's our triangle. And remember, we have this height that's 139 meters. So we're going to calculate AN first. Remember, we said AN is going to be half of AC that we found earlier, and AC was 325,27 meters. We're going to divide that by 2, and now we have our value for AN. So AN is roughly equal to approximately 162 meters. Now, because we have both sides, we have an opposite side, and we have the adjacent side, we said we're going to use a tangent function. So tangent of theta is equal to MN over AN, and we're just going to plonk those values in there that we found. So 139 over the adjacent that we found. And using second function tan of our answer, we're going to end up with our angle theta being roughly equal to 40,5 degrees. So these calculations should be quite easy. Okay, so as you can see, the calculations themselves are not very difficult. It's just identifying what the 3D figure looks like and which part of the 3D plane you're working with. Okay, let's continue. Okay, here's our next example. In this example, bird stands at a point B on the ground. The angle of elevation to the top of the cliff from B is 38 degrees. So we're talking about the angle of elevation, so it's the angle from the horizontal upwards is 38 degrees. And because we're talking about the horizontal upwards, we're going to notice later that this angle is going to be a 90-degree angle. Okay, and Dan stands at D, which is 685 meters away from B. C is at a point at the base of the cliff. So because C is at a point at the base of the cliff, we can join those lines. And Dan estimates that the angle CDB is 42 degrees. So this angle between the cliff and B is 42 degrees. He wants to know what is the height of the cliff H rounded to 2 decimal places. So we need to find this. Okay, so this is a pretty simple 3D diagram because we only have 2 planes. We've got the horizontal plane, BCD, that's that one. And then we have the vertical plane, that's ABC. So ABC is a right angle triangle, which means we need to have 2 bits of information for ABC. As it stands, we only have the angle, so we cannot solve that triangle. But if you look at the triangle CDB, we've got 3 bits of information. We've got 2 angles and a side. Can you remember which rule we should use here? I'll let you think about that for a while. Okay, have you thought about which rule we can use? Okay, there's a bit of a problem here because we don't have a matching pair and we don't have side angle side either. But if you notice, we do have 2 angles, which means we can easily find this third angle here, and once we find that third angle, we will have a matching pair because we'll have an angle and its opposite side, which means then we can use the sine rule. So let's begin by finding angle DCB. So remember, it's going to be 180 minus 42 minus 63 degrees. So it's just going to be 75 degrees. So because this angle is just going to be 75 degrees, we can use the sine rule. And remember again, we're going to use the sine rule because we want to find BC. We need one more bit of information in this triangle to solve this triangle. Because if we find BC here, then we can use AC over CB. So we'll have the opposite and the adjacent sides of the right angle triangle. And then we can use tangent to solve for H. So back to our triangle BCD, we've got our pair and we need to find BC. So we're going to start off our equation with BC in the numerator. So using the sine rule, we're going to start off with BC in the numerator. So BC over the angle across from it, and across from BC, we've got 42. So BC over 42 must equal to 68.5 meters over the angle across it, and the angle across that side is 75 degrees. That's the one we just found. Okay, we've got to just rearrange this to get BC. So BC is equal to 68,5 times sine of 42 over sine of 75. And then it's pretty simple. We're going to just put this into our calculator. Let's just do that quickly. Okay, so we're going to say 68.5 times sine of 42, and that's going to be divided by sine of 75. So our answer is going to be 47,4523. Okay, and remember, because we want to find, oh, sorry, I haven't written the answer. Let me just call out my calculator again. Okay, we're going to keep that in answer in our calculator, that 47,54523, because remember we're still continuing with the sum. So instead of rounding off and leaving the answer, we will continue with the answer with all the decimals on our calculator. Okay, then we said we're going to use 10 of 38 to find the hypotenuse. And remember, 10 of 38 is equal to h over BC. So 10 of 38 is equal to h over BC. So, but remember, we're going to rearrange this so we can make h the subject of the formula. So h will equal to BC times 10 of 38. And remember, this is the value we have in our calculator at the moment. So we just have to multiply that by, so there's our value in our calculator, our value for BC. And now we've got to multiply it by 10 of 38 degrees to get our value for h. So our value for h is approximately 37,0738. Okay, so BC times 10 of 38 is approximately equal to 37,0738. And remember now, because we've substituted that value for BC into the calculator, you could either have done it in one step, like this, or the way we did it earlier, and you're rounding off to 2 decimal places, so it's 37,07 meters. Okay, it's time for a quick air break. See you just after this. Okay, welcome back. So before the break, we were discussing 3D trigonometry, and we dealt with vertical and horizontal planes. We're going to extend that a little bit now to include inclined planes. So what is an inclined plane? Let's take a look. Okay, look at this diagram where we have A, B, C, and D. So we've got 2 vertical planes, the 2 blue planes. So I can separate them because remember that each of these planes will now give me right-angled triangles. So angle ADC, triangle ADC is a right-angled triangle, that one, okay? And similarly, triangle BDC is a right-angled triangle and right-angled at D. So those 2 triangles are right angled because the vertical plane is perpendicular to the horizontal plane, so it produces that 90-degree angle. We've got 2 other triangles. I'm not sure if you can see both, but the green one's pretty obvious. It's kind of like the ground or the base of our room. So it's, remember I told you, try and picture it like a room or the corner of the room. It makes it a little bit easier sometimes. So this is the floor. So this green piece here will be our floor piece. Okay, so basically it looks like this. And as it stands, it's not necessarily a right angle triangle. It depends on whether it's a corner of the room or whether there's some kind of a mass. So we cannot always assume that the angles are right angle. It may not be a corner of the room necessarily or not be a perpendicular corner. So usually this triangle on the base is not a right angle triangle, and we'll have to use our trig rules to understand it. So remember, alpha is in this triangle here on the base triangle. And so when we're redrawing it, we'll draw alpha like that. Okay, and the last triangle is this triangle that beta is sitting in. And if you look at how we've labeled beta here, it's the angle across here. So it's part of this triangle here, this larger triangle here, which is kind of inclined, and you can kind of picture it to be, as if like a tilted roof piece. So this triangle ABC is in the inclined plane, and beta belongs to this triangle here. And remember, this triangle A is quite different from alpha and theta. It has nothing to do with alpha and theta because it belongs to a completely different triangle, as we will see. Okay, sometimes it does help to make an actual model of a 3D plane, of a 3D diagram, just so you can kind of look at it and, from all sides and understand where the right angles lie. Okay, let's continue. Okay, in this example, we've got a regular block of wood which has a breadth of 6 centimeters, a height of 8 centimeters, and a length of 15 centimeters. Okay, and a plane is cut a plane cut is made through the block as shown in the diagram, revealing the triangular plane that has been formed. So basically, we've chopped out this corner, and we left with something like this. Okay, so we've got a block of wood that looks like that. They want us to calculate the size of EBG. So EBG is part of this inclined plane here, and this is the question they want us to find. Now, if we look at this diagram, we realize we've got nothing in that red triangle at all. So we've got to think about what we're going to find first while we're trying to find this angle. Remember, if we find all three sides of this triangle, that means EB, EG, and BC, then we can use the cos rule to find angle B. So to find each of these angles, you'll notice each of them are sitting in a right angle triangle. So we can begin by finding EB using this right angle triangle here, EAB, which is right angled at A. And we're just going to use Pythagoras. And we'll repeat the process with each of the other triangles as well. So triangle BCG, and again with triangle EGH. Okay, so that's how we're going to start our calculations. Okay, so we're going to start off with EB squared, and that's easy. It's just going to be 8 squared plus 6 squared, and we're going to get 100. So in other words, EB will just be 10. Similarly, in triangle GBC, we've got 15 squared, and this side is also 8. So 15 squared plus 8 squared will give us 289, and we find the square root of that, and we end up finding that this side here is 17. And remember, we found this was 10. Okay, we've got one more to find. We need to find EG in the top triangle. So EG is equal to, this side here is 15 squared plus the width is 6, so 6 squared. So we can find EG by using Pythagoras here. So it's 15 squared plus 6 squared, so it's 261. But again, remember, we want EG, not EG squared, so we've got to take the square root. And since we cannot find the square root of 261 easily, we'll just write it in that form. Okay, now, we found all three sides. So we've got 10, 17, and 261. Now, we've got to use cos rule to try and find this angle. So because we want to find this angle, we're going to use the side across it as well. Remember, that's what we're going to use. We're going to use the V pattern here to write out the cos rule. Okay, so let's begin writing out our cos rule. Okay, so we found that EB was 10 units, BG was 17 units, and this was the square root of 261 meters, or units. Sorry, it was centimeters in this case. Okay, and remember, we needed to find this angle here. So because we want to find this angle here, we need to start our cos rule with the side across it. So when we're beginning our cos rule, we're going to be using, we're going to be starting with square root of 261. Okay, so basically, if we want to find the square root of EGB, it's going to be square root of 261 is equal to, and then we're going to use this side squared, so 10 squared plus 17 squared, and then the angle between the two of them. So it'll be 2 times 10, 17, and the angle between them is angle EBG. So the cos of that angle. Remember, because we wanted to find out EBG, we had to start the cos rule with the side across from EBG. Okay, so rearranging this equation, we've done this a lot of times in the previous sessions. You should know that it's going to be 17 squared plus 10 squared minus 261 over 2 times 7 times 10. What's left now is, remember again, because we're using cos rule, we need to use our calculator to find this. And in order to use our calculator to find an angle, we've got to use shift cos. So basically, we've got to have that. And if we plonk that into our calculator quickly, we should have, so we want to find second function cos, and it's going to be 17 squared minus 10 squared, plus 10 squared. Let me just correct that. and then minus, and the square root of 261 squared is just going to be 261. And at the bottom, we've got 2 times 17 times 10. And so our answer for our angle EBG is 67,8847. We want to round it off to 2 decimal places. So we're going to get 67,88 degrees. Okay, we're going for a quick ad break. I'll see you just after this. Hi, welcome back. Before the break, we were dealing with 3D problems. So let's continue with another example. Okay, in this example, they tell us that in the diagram, AB is a straight line 1,500 meters long, a vertical tower 158 meters high with C, A, and B are points in the same plane, and the angle of elevation from A and B are 25 degrees and theta, and they've given us that CAB is 30 degrees. So the angle of elevation, let me just grab my pen. Okay, so the angle of elevation from A, they're talking about this angle, which is 25 degrees, belongs to the right angle triangle ACB. They're telling us the angle of elevation from B, which is theta, belongs to the triangle DCB, and that's a right angle triangle. And in both these right angle triangles, we've got 158 meters being the opposite angle. And they've given us that 1,500 is the line AB, and it belongs to this green triangle, which is our horizontal, on our horizontal plane at the base. And the only bit of information we have for this triangle is 30 and 1,500 meters, which means we only have 2 bits of information, which is not enough to solve a non-right angle triangle. But these 2 triangles, we do have enough information to solve the right angle triangles, because remember, we need for this ADC, we have 2 bits of information. Here we only have 1 bit of information. We've only got 158 meters. So the triangle we can solve as it stands is triangle ACD. Okay, so determine the length of AC correct to the nearest meter. So AC belongs to that right angle triangle. And remember, we've got to use, because we want to find AC, we're going to use opposite over adjacent. So we're talking about 10. So 10 of 25 degrees will equal to 158 over what we're looking for is AC. So rearranging this, AC is equal to 158 over 10 of 25. And so AC is roughly equal to 338.8 meters. Okay, and because we now have a value for AC, let's look at the next question. Okay, AC is roughly, they did ask us to do it to the nearest meter. So 338.8 becomes 339 meters. So roughly AC is 339 meters. Okay, they want us to find the value of theta correct to the 2 decimal places. Now, to find theta, we have a bit of a problem, because we did say we don't have enough information in this triangle here. So we're going to use the base triangle to first find BC. And once we found BC using the green triangle, we can then use opposite and adjacent to find theta in triangle CDB. So let's begin by looking at this triangle here, triangle BCA, and trying to find angle BC. Remember, we found AC to be 339 meters in the previous slide. Okay, so we've got AC, we've got this side here, and we've got the angle in between. So it looks like we've got side, angle, side. So we can use cos rule, and we can use cos rule to find BC. So let's begin writing out our cos rule with BC squared equals to, and remember, because we're starting off with BC squared, we've got to write BC squared is equal to AC squared plus AB squared minus 2AC AB cos of CAB. Remember again, you're starting off with BC, you're ending off with the angle across from BC. Okay, and we're going to plug in all our values that we have. So AC squared is 339. AB squared is 1,500. Okay, and then we're going to put in 339 back in here, 1,500 in here, and CAB was our 30-degree angle. Okay. Okay, so in other words, we're going to find BC squared roughly equals to about 1,484,173. And remember again, we're looking for BC, so we're going to find the square root of that. And because the sum is continuing, we're actually going to keep that in our calculator's memory, because we're going to use that in the next step. And remember, the next step we said we're going to use this triangle to solve it, because now we have a value for BC in our calculator stored, which is this value here. Okay, so we're going to use 10 because we've got opposite over adjacent. So we're going to say tan of theta is equal to DC over BC. So it's going to equal to 158 over this, not 128 actually, we're going to use 128, the value that we have in our calculator. Okay, so it's a value that's stored in our calculator. And we're going to say 128 over this value BC that we have stored in our calculator. And we're going to find shift tan of that answer. And once we do that, we're going to end up with theta equals to approximately 7,3895 degrees. We're rounding off to 2 decimal places like they asked us. So theta will equal to 77,39 degrees. Okay, so there's another question, and they've asked us to calculate the area of triangle ABC. So they want us to calculate the area of this base angle here. So that's pretty simple, because remember, we already found this to be 339 degrees. And what do we need to calculate area? We need side, angle, side. So we've got this side, we've got this angle, and we've got this side. Remember, we're always looking for a kind of a V pattern. We've got side, angle, and a side. So we can find our area. So our area will be half AC times AB times sine of the angle in between, which is 30. All that's left to do is now put in our values. AC is 339, AB is 1,500, and the sine of 30. And I think the calculator work in this one is pretty simple, so I'm not even going to do it right now. We're going to end up with our area being 127,125 meters squared. Okay, this one now involves the inclined plane. They tell us if AD is equal to 374 meters, so they're giving us the value of this side here, okay? And they're giving us the value of BD to be 1,229 meters, okay? And they want us to calculate the angle ADB. So they want us to calculate this angle here. So basically, we're dealing with the inclined plane like this. So this one here is 374 meters. This one here is 1,229 meters. And we know that this is 1,500 meters. So because we want to find this angle, we can use cos rule. And how can we use cos rule? We start off with the side across the angle we want to find. So our equation for cos rule is going to start off with 1,500 meters squared. Okay, so it's going to start off with 1,500 meters squared equals to that squared plus that squared, so 374 squared plus 1,229 squared minus 374 times 1,229. And remember, because we started off with 1,500, we're going to end up with the angle across it. And the angle across it is the angle we're looking to find. So the first problem again is to rearrange this. So remember, when we're rearranging this, we've done this lots of times before. Okay, so cos ADB will simply be 374 squared plus 1,229 squared minus 1,500 squared divided by that. So 2 times 374 times 1,229. Okay, and again, because we're finding cos, we'll have to put this into our calculator, and we need to put this into our calculator using the shift cos. And so it gives us an angle of 130.7176. And remember again, we've got to round this off. So we end up with roughly around ADB being roughly around 130,17 degrees. Okay, let's try a similar example, but this time we're going to be using variables instead of numbers. So this is a very similar question in terms of the way it looks, but here they tell us to determine the length of dB in terms of y and theta. So they want us to find the length of this side using theta and y. Let's just examine our diagram quickly just so we understand what's happening in this diagram. They've given us DC is y, okay? Theta is the angle from here, theta is the angle from here up that way in the pink triangle. Alpha and beta are part of this bigger inclined plane here. Can you see that? So alpha and beta are part of this triangle ABD, the inclined plane, the triangle that's sitting on the inclined plane. But at the moment, all they're asking us to find is dB in terms of y and theta. So we're going to be using the right angle triangle, the pink one. So basically, we've got the right angle triangle like this, and we've got theta, and we need to find dB in terms of that. And dB is the hypotenuse, so it should be easy enough to find. Okay, so let's begin. So sine of theta is equal to opposite over hypotenuse, so it's y over dB, okay? And so dB is just y over sine of theta. So we've answered that question. Pretty simple. But the reason they're asking us this is we're probably going to use this in the next part of the question. Okay, so we use the pink triangle to find dB as being y over sine of theta. The next part of the question is they want us to show that AB is equal to some complex expression, y sine alpha plus beta over sine theta sine alpha. Now that sounds complicated. Let's just look at what they're asking us to do. They want us just to find AB. Let's go and see where AB is and what information we have to solve AB. So basically, if you look at AB, AB is this one here. And AB lies in this inclined triangle ADB. So it lies in here. And in here, we already have that, and we already have that, and we've just found this side DB, which means we've got two angles, and we've got a side, we've got one matching pair of angles inside, which means definitely we can use the sine rule to solve it. Okay, so in this triangle here where we have AB, we first got to find, okay, so we have to start off, if we look at this triangle here, we've got alpha, we've got beta, and we've got this side. So we've got one pair of matching sides, so we decided we're going to use sine rule. The problem is we need to find AB, okay? So because we want to find AB, we need to have that angle across from AB. And that's easy enough to find because we've got alpha and we've got beta, and we're going to use three angles of a triangle. So that's where we're going to start off our calculation with. Okay, so again, let's recall we were trying to find AB. But if you look in this diagram, we don't have the angle across from AB, which is ADB. But it's easy enough to find because we have alpha and we have beta in the same diagram. So basically, in this diagram, we've got alpha, we've got beta, and we can find that pretty easily. Okay, we're going to use angles of a triangle to find that one. So let's begin there. And then remember, when we're using the sine rule, we already have this side, and we have a version of dB, which we found in the previous slide. So basically, first we're going to find ADB, and ADB is going to equal to 180 minus alpha plus beta. Now we're going to use the sine rule in our triangle, like we said, and because we want to find AB, we're going to start off with our sine rule with AB, and AB over the sine of the angle across it. So it's sine of 180 minus alpha plus beta, because that's the angle that's across from AB. Here's AB, and the angle across it is 180 minus alpha plus beta. And the other matching pair that we have is dB over the sine of the angle across from dB, which is alpha. Now remember, we had dB earlier, isn't it? We had dB, we found out dB in the previous slides, and we had dB was equal to y sine theta. So we're just going to substitute therefore dB in the same equation. But at the same time, we're also going to realize that this sine of 180 minus beta can be simplified because this is now second quadrant. And in the second quadrant, sine is positive, so we're going to use our reduction values to say sine of 180 minus alpha plus beta simply gives us sine of alpha plus beta. And if you want, you could have put a positive, but because it's in second quadrant, we need to check the sign, and the sign is positive. Okay, so now we have an expression for AB that looks kind of complicated. AB over sine of alpha plus beta equals y over sine of theta over sine of alpha, and we need to make it look like this. So it just requires a bit of algebra to finish off, and we're just going to first multiply by sine of alpha on both sides, alpha plus beta, and there we go, we've multiplied the right-hand side by sine of alpha plus beta, and now we're going to just do a little bit of cleaning up. So this becomes y over sine of theta divided by sine of theta because of that. All right, and remember, a division can become, you invert and multiply, so it becomes times 1 over sine theta, because we're going to, this is the same as sine theta, sine alpha over 1, so it's going to become 1 over sine of alpha. And now we kind of have only multiplication, so if you multiply all the numerators, y times 1 times sine of alpha plus beta, it's going to give us y sine alpha plus beta, and the bottom we only left with sine of theta times sine of alpha. So writing that all out, we're going to end up with y sine of alpha plus beta over sine of theta times sine of alpha. And that looks exactly like what they've asked us to prove in the first place. And that brings us to the end of this question. Okay, that brings us to the end of this lesson. Thank you for joining me. Please join me in the next lesson when we extend this concept of 3D trig problems into including using your compound identities. That's all for now. Bye.